So after the talks of the past 3 days, I don't think I need to motivate that we need to go to beyond 2-point statistics. But I'll try to briefly summarize the major points. So the late-time large-scale structure is highly non-Gaussian, and power spectrum is not enough to describe it completely. So to visually see this is the large-scale structure. Now we keep the same power spectrum, but scramble the phase so that all the phase space correlations are washed over, and this is what you get. So obviously there is more information in the large-scale structure than the power spectrum. Also, with the ongoing and upcoming surveys such as Euclid and DESI, there is going to be a lot of information on small scales, and we have to be able to extract as much information that we like from it. So people have talked about multiple things such as field level inference, more physically motivated statistics such as k nearest neighbor, Voronoi volume function, mark correlation, and much more. What I'll talk about is getting information from the morphology of the cosmic web, wherein we look at the objects in the cosmic web and see what structure they have statistically. So what will this achieve? Approaching the same problem from multiple ways, you could get better constraint, you could possibly break the tensions in cosmology, and especially with the large scale structure, you could probe the nature of dark matter. So this image is similar to what the background of the poster of this conference looks like. So the cosmic web acts as a bridge between the very early universe and the late universe. Not only that, it lies somewhere in between the very large scales which you can describe using perturbation theory and the very small scales wherein you could apply virial theorem and things like that. And finally, it's a bridge between observations and theories, the very basic theories of the universe. What you see is this, but the model of the universe or nature of dark matter, nature of gravity will influence what the large scale structure looks like, and which in turn will affect the formation of galaxies and their evolution that we actually observe. So here is a movie of the evolution of the large scale structure, and you see that the skeleton of the cosmic web is placed in the very early universe, and as time progresses, what happens is the nonlinear regions become more and more nonlinear, and the cosmic web becomes more and more prominent. Yet the skeleton is laid out in the very early universe. So let's move to more literal bridges, which are filaments in the cosmic web. So broadly, the cosmic web is classified into 4 regions. There are large underdense regions known as voids. Around these voids are 2D structures known as sheets or walls. Where multiple such sheets meet, you have elongated regions known as the filaments, which are the most prominent features when you look at the cosmic web. And at the ends of these filaments are dense nodes. So filaments are these elongated structures which join the nodes. And this is a zoom in onto the last movie, but I have zoomed into a more dense region. And what you can see is that matter gets accreted onto these filaments and is moves along these filaments onto the nodes. So these act like cosmic highways, and they have implications on galaxies and halos. So, okay, this looks pretty, but why do we study it? People are interested in multiple things. The cosmic web is, or filaments specifically, are very anisotropic. So they affect tidally the halos that form within them. People are interested in up to what order the halos are affected because of these filaments and how. People have also seen that because it accretes and feeds gas into the nodes, star formation rates are affected because of filaments. So are galaxy formation, evolution, morphology of galaxies, orientation of galaxies, and much more. Also, the missing baryon problem, wherein around 40% of the baryons today aren't observed. Those are supposed to be present in these filaments in the form of the warm hot intergalactic medium. So many observers are interested in filaments. Now more cosmology point of view, Understanding the dynamics of filaments will provide insights into how the large-scale structure formed and evolved. And also, the nature of dark matter affects the large scale very strongly. For example, warm dark matter will wash over substructure in the filaments. So understanding them better will provide insight into the nature of dark matter as well. What I'm interested in is looking at the dark matter filaments in phase space and to see if some kind of universality exists in them. So it's a well-established fact that the dark matter halos follow this NFW profile, wherein more or less any halo you take in the simulation, it will be described broadly by only two parameters, mass and concentration. So here is one halo from a simulation, and you see that the fit is really good. Note that this is not a stack, it's a single object in the simulation which can be fit by a function with just two parameters. So it is natural to ask that does such kind of universality exist in filaments in the simulations? And what do we expect? So broadly we'll expect filaments to be dense in the middle and they should go to the mean density of the universe, not as dense as halos because they are not completely virialized structures, but more or less such kind of profile. In terms of velocity, we also expect infall onto the filaments, and as we go along the filaments, we expect stuff to move towards the nodes. And when we look at the full phase space, we expect to see some kind of caustics there, which will provide us information about the boundary of the filament. Apart from just the fact that it is interesting to look at these profiles and do they obey universality, understanding them will provide insights into how the large scale structure formed and evolved to start with. Maybe if we could quantify the any filament profile by a few quantities, the distribution of those quantities might change as we change the cosmology or as we change the dark matter model. And using these, we could probably put constraints on cosmological parameters and almost surely put constraints on the dark matter models. So what do we need to calculate these profiles? Like in case of a halo, wherein you'll need the center of the halo, in case of filaments, you'll need the spine of the filament, which is analogous to the axis of a cylinder. So this here I have shown a density slice of n-body simulation, and I have applied disperse, which is a widely used filament finder, and this gives the filaments. They look pretty good. Why not just use them and go ahead? There are many issues. First of all, multiple filament finders exist in literature, each based on a different concept, and when applied to the same data, it gives you a different set of filaments. So for example, disperse, it uses Morse theory and persistence to find ridges in the density field of the density field. Nexus uses eigenvalues of Hessians of different quantities such as density or divergence of velocity, etc. And there are many more. The problem exists because there is no consensus on what defines a filament. Is it a ridge in the density field? Is it something related to the velocity Hessian? We do not know. But let's pretend for a while we know what it is. And we know, okay, this is the filament finder that has got the definition of filament right. Even then there are problems. So when you stick to a single filament finder, it is associated with multiple free parameters. And the way they are fixed is you apply the filament finder again and again with different parameters, look what the filaments look like, and the visually correct choice is the one you choose. So obviously this is not the most principled way to go ahead. And why the problem arises is that it's a chicken and egg problem. Unless you apply a filament finder, you do not get a filament. And unless you have a filament, you can't check how good your filament finder is. Right? Apart from this, there are complications arising because of substructure that is there in the filament as well. Now we try to solve some of these issues. So first of all, we solve the chicken and egg problem by creating mock filaments. So you could create multiple filaments, particle realizations of filaments, different kinds of curvatures, node masses, etc. Apply the filament finder again and again with different parameters. And now since you know the truth, you know how good the filament finder is. This will fix the parameters for you. Not only this, now that you know the truth, you can study biases in the profiles that you extract. And one of the major things we find is that curvature plays a very important role in the biases that you get in the inferred profiles. And unless it's not good to stack all the filaments without considering the fact that there is curvature, otherwise you'll get very biased profiles. This is an example of a simple filament generated. And another problem is that once you say you have fixed all the filament parameters, filament finder parameters, still inherently there will be noise on the filament spine and you need to smooth it. And this noise varies as you change different kinds of filaments. And because of the inherent hierarchy in the filaments, these noise properties are different. So the usually used smoothing, which is known as nearest neighbor smoothing, does not work. So we solve this by introducing a new kind of smoothing, Fourier smoothing, which is basically you go to Fourier space, apply a low pass filter and come back. This is pretty much insensitive to the choice of parameter that you make, as well as a single parameter works more or less for all the filaments. Also, the parameter that you choose is more physically motivated because it's a length scale in the problem. We also add an optimization scheme wherein the parameter of smoothing can be fixed by looking at the density profiles. I don't have time to go into depth, but I'll talk over it. So we just focus on the left hand side plot. We have generated filaments of different properties, applied different kind of smoothings, and we look at the length of the obtained spine by the true length, its profile, its distribution. So what you expect is ideally a Dirac delta function centered on 1, and you see that combination of optimized smoothing along with Fourier smoothing technique gives you a pretty good result. Now we apply all these techniques to simulations and see what happens. Well, these are the density profiles and these are the velocity profiles, and I have taken the same simulation, the same redshift, and given different inputs to the filament finder like dark matter particle positions, density grid, halos, etc. And you see that there is no convergence, no agreement between anything, not just in the inner profiles but in the outer profiles as well. This is happening because you haven't, probably happening because you haven't taken into account the inherent hierarchy of the filaments, and using different inputs, you are identifying different kinds of filaments and you cannot really compare across those. So we are developing a new filament finder based on Voronoi tessellation, which will take into account this inherent hierarchy of the cosmic web. So a tessellation is something that covers the whole volume by region such that there is no overlap, neither is there any gap. And Voronoi tessellation is created such that you have a set of tracers. It splits the whole space into cells such that every point in the cell is closest to this tracer as compared to any other tracer. This is not something new that we have come up with. It's been used in cosmology for decades. A more intuitive way of looking at the Voronoi tessellation is you sit on every tracer and start growing spheres. Every time two or more spheres intersect each other, you freeze that point so that you end up with the Voronoi tessellation. You see that these cells have information about the environment of the tracer used. For example, where there are a lot of tracers, the volumes are very small, and also they hold information about the anisotropy of the cells. For example, here you consider, say suppose I consider this to be a filament. In filament, you consider it to be like beads on a string. The cells will be squished along the filament direction and not squished perpendicular to it. So we use this anisotropic information encoded by the shapes of the Voronoi cells to construct a filament finder. So here I have given a very rough dark matter density field through an n-body slice, And here you see the Voronoi tessellation, and it's obvious that these pancake-like squished cells can be joined together to form these filaments. To include the hierarchy, what we do is we progressively go down the halo mass. The most prominent filaments are supposed to be joined to the most massive halos, and the spine will also be constructed by comparatively massive halos. So we'll find these first, we will go down progressively and delete these filaments as we go down, so that you'll obtain the hierarchy of the filaments, and then you can look for universality in a more better way. So thank you for listening. I'll be happy to answer questions.
Question? Thank you for nice talk. How will you use the velocity information in this Voronoi kind of thing? Because it looks like only density field.
Yeah, so we were hoping to construct a filament finder which can be applied to observations, so no velocity fields. But then including it really helps. For example, I will ultimately want to define the full volume of the filament itself, and the velocity, the infall velocity, gives you a parameter independent way of defining the radius. So we'll include it, but we'll construct it such that it can be applied to observations as well.
But you will use the same thing like Voronoi in
Yes.
velocity space?
No, we'll use density. Voronoi will be constructed only in density space, but we'll use velocity information to look at its extent.
Okay, great. Thank you.
Thanks a lot for this very nice talk. So maybe you already said this. So how do you decide the number of tracers as well as the distribution of the tracers?
So I haven't said this, and we are still thinking about it. First of all, the distribution will just put a cut on mass or any other quantity such as the V peak or something like that. And ideally, we would like to construct it such that since we'll progressively go down this quantity, the threshold that we choose at each step shouldn't matter, so that finally we'll get a set of filaments which is independent of, not independent, least sensitive to the thresholds that we choose.
Thank you.
Thank you for the nice talk. So if you do you care about the width of the filament, and if so, how would you find it in this sort of algorithm?
Yeah, so I do care about the width. So I'll first get the spine, I'll process it so that it's smooth enough. Then I'll look at its radial profile, and when you look at it, you'll see that although these are not very trustworthy results, you will see a very strong dip in the infall velocity at the edge of the boundary of the filament. So you have the spine, I'll construct a cylinder, curved cylinder around it of this radius, so that I know what the whole object looks like.
About connecting the Voronoi regions, since you already have the Voronoi tessellation, you can just look at the Delaunay triangulations.
Yes.
Because then the Delaunay triangulations will actually give you the directions. The longer sides of the Delaunay will give you the filaments.
Yeah. So actually, more than that, so that does help. But if you look at construct inertia tensor of the shape of the cells, it provides you way more information about the anisotropy itself.
Yeah, Delaunay will be the first guess. Then you
exactly.
use,
Yeah, so right now we are using the tensor to start with. Yeah, so of course Delaunay will help, but then it will connect everything. So
yeah, then
it
you
will
have
also
to choose
connect
which
these
ones you
for
need.
that. Yeah. So I have to put an anisotropy cut some point.